Hello friends, today we are going to discuss on welding procedure specification, what it contains and what are the essential parameters to be written down and how well we should write it down so that tomorrow in our absence if somebody wants to follow our welding procedure specification, he should be able to understand almost 99% and 1% chance only will leave it to him for his discretion depending upon the situation. So to do that, let us first understand what is welding procedure specification. It is more like in PDCA cycle our plan as to how we will be executing a given joint, what consumables, what parameters, what kind of edge preparation, how are we going to use, what are the essential variables as per code, and how are we going to really achieve a successful joint. So it is a planning sheet which is prepared by a welding engineer. So first he has to understand what is the material which we are going to weld. So we'll go step by step and see the format which is prescribed by section 9 ASME, and it is also approved by AWS, accepted by many of the fabricators and the consulting agencies or designers in the world. So obviously any document will require a number, so I don't have to elaborate on the mandatory requirements, the revision number, the welding process, because we are writing a procedure, so it has to be a process specific. It can be a combination of 2 or 3 welding processes, so we can write the details of each of those processes, the names. GTAW is for the gas tungsten arc welding, SMAW, MAG, MIG. There are many versions in which we can write it. It's not mandatory to follow, but good to have an organization writing in a particular way. Next is a welding process type, that is manual, robotic, automatic, with column and boom, with positioner, with rotator, with other kinds of manipulators, whatever is actually going to be used by using this WPS, which has a unique number. Now both of them, the welding process and the welding process type, are essential variables. That means if you change any of this process or the type of the process, we will have to rewrite the WPS and we will have to submit it to a third party inspector or customer rep or to our approving agencies, whether internal or external, and get our proposal, the plan, approved so that we can go towards a PQR. PQR is a set of parameters which will be recording on a particular thickness material which is given in this WPS, and try to qualify. That means whatever is our plan, whatever we have envisaged, that this base material, this filler wire with all the welding parameters will give us the required results that will be demonstrated in a PQR. So the efforts which are required, or the thing which is to be kept in mind, is that for a WPS, when we are writing it for the first time, it is kind of a proposed WPS with all the discussions and visualization of what is actually going to happen on the fabricated item or equipment. We are going to do certain changes. As we go further down onto the list of WPS, we will discuss about them. Then the very important portion next, which is highlighted here, is the joint type and joint design. So what we mean, and there will be a sketch which will be coming up of this particular joint type and this. So here it is a groove type, groove weld, or a fillet weld, or a combination of a groove and a fillet weld, and how this particular joint, we'll have to look into the sketch of it. When we'll go to that portion, we'll talk about it more, whether the joint has a backup ring of the same material, different material, So it is listed in backup and material. Once again, having a backup or not having a backup, depending upon the material in the code, we'll have to see whether it is an essential variable or a non-essential variable. But what we have to understand is that if we are using a backing and qualifying a WPS, and then even if the code allows us to use the same WPS because backing is not an essential variable, I will not strongly recommend to use it unless we make another PQR without a backup. The importance for here is that if we are not able to penetrate, the most important part in the root run is how well we are able to penetrate, how well we are able to fuse. Now you will say that this can be seen in a WPQ also, the welder's performance qualification. When we are going to do it, this will be discussed and this will be seen. But when especially the impact tests are required, I think it is essential to have a backing as an essential variable. Having backing or not having backing, we must re-qualify our process, and also on the type of material. Having a ceramic backup, having a copper backup, having a same material backup or a different material backup, I think things may change and vary. So it is good to have a consistency, uniformity, especially when we are going to have difference in our impact requirements or other supplementary requirements. And for the critical materials which are not in P number 1 to 5, as we will go further, we will see the P number also in this video or the next video. Then on the right hand side, here we have whether we are going to have a preheat. Are we going to heat the joint by a different method, electrical method, a gas burner or infrared, and to what thickness and to what temperature are we going to do the heating? Generally up to 25 millimeters, no preheat is recommended for carbon steel, but if it is aluminum, even for 6 to 8 millimeter, you will require a preheat because of its high conductivity. So depending upon the material and the thickness, you will select a preheat. Similarly, the preheat temperature. And the recommendation here is that if you are welding from the front side, the preheat should be as far as possible given from the other side of the welding, so that when you check the temperature, whether it has come with your temperature sticks or by infrared, the whole cross section, the whole thickness of the material gets preheated, and also it gives a uniformity. That means it distributes the heat in all directions. It's not only coming up from the bottom of the plate, but it is going sideways also. And the entire area which is going to see the heat affected zone and a temperature zone which is going to be higher than the room temperature shall be preheated when you are going to do a welding. Next is coming the interpass temperature. Now, what is the meaning of an interpass temperature? When you finish your one pass or one layer and then want to start the next one, either by a stick electrode or by any process of welding, before you start the next, or it also has a meaning that when you are welding roughly, now it is a thumb rule that about an inch, 25 millimeters away, we will be having very high temperatures. But as you go further to maybe 50 millimeters or 75 millimeters, you will start seeing that the temperature comes to either a preheat temperature or to a room temperature. And we should have a check somewhere between the weld point and your point where we are going to have a room temperature or a preheat temperature. So that temperature during welding or during a pause and when we are going to start the next run, that temperature is called as the interpass temperature. That means before we start welding or during welding, half the distance between melting point or the weld point and the room temperature, half the distance shall not go beyond the interpass temperature, or we should not start welding when the earlier pass has not fully cooled down below the interpass temperature. This has an impact on the grain growth. This has an impact on our the impact energy, the absorption of energy, what we do it. And does this preheat requires a maintenance, or in other words, is it the post heating? And how much time this preheat shall be achieved? That means as soon as the temperature is arrived, like we keep in heat treatment furnace, our annealing temperature or stress relieving temperature is, let's say, 900 degrees centigrade or 600 degrees centigrade. As soon as your material reaches to 900 and 600, you don't stop it, because after that you want to really achieve the uniformity across the thickness, so you have a soaking period. So similarly, the preheat maintenance is required to be looked into two ways. One is that as soon as the temperature is achieved, are you going to start welding, or are you allowing it to soak for 5 minutes, 10 minutes, 20 minutes, depending upon the thickness, material, welding process, environmental conditions, and then start the welding. And once the welding is complete, we have to ensure that the preheat temperature is retained for that time if there is no separate post heating. If there is a post heating, obviously we'll start onto the post heating requirements as we move further. So this is as far as the joint type and the parameters as far as the temperature conditions to which we are going to start working and start welding. The next essential variable comes in is the base material. Now there are two materials which we are joining, so base material 1 and base material 2. There could be 3 materials. We can add one more column and have a tri-junction joint where 3 parts are coming together and getting welded in the given configuration. Now for each of this part, we need to write the P number. P number is a classification of materials, and within the P number, the adjustment or the arrangement is such that we have P numbers which are arranged based on the welding, the metallurgical characteristics of that particular alloy. So carbon steel with different percentages of carbon, with no alloying element, or with minor alloying elements or major alloying elements, or a different material like stainless steel which has deliberate additions of nickel and chromium and has completely different properties. Or we have different alloys altogether, not the ferrous alloys but nickel based alloys, titanium based alloys, cobalt based alloys, aluminum based alloys, or combination of that are getting classified in different P numbers. So since the material is changing drastically, it is essential variable in our WPS or PQR. Next is a group number. Group number actually deciphers within that similar characteristics of welding or similar type of alloy, but the strength requirement is from 60,000 psi to 70,000 psi, or the impact properties are added, or there are certain other properties or essential requirements, physical requirements which are required to be met, then the group number changes. Higher group number qualifies for the lower. All those essential things we will see in great details later on when we will be talking about section 9 or section 2C, when we will be talking about the consumables. So the P numbers are essential variable. Group number, as I said, are also essential, provided you have a higher number which qualifies for the lower ones. And for both the alloys or as many alloys getting welded simultaneously, the base material 1, 2, 3 has to be listed down, and any change in any of the material will ask us to qualify for a new. Now we are talking about the specific grade. Now this particular grade is not listed into ASME section, hence P number is written as not applicable. So where we are not able to classify into the right P numbers, because these are all some special alloys not listed in ASME section 2 or section 8, then those are either we can give the nearest number, but when we give the nearest number, then we'll have to write the nearest P number is so and so, and also give the specification or the grade, like here it is PT3B unassigned P number, that's the nomenclature which has been used, and the form in which we are going to use it. The form is like already described here: plate, tube, pipe. This is very essential to write down this form. I will also advise that not only plate, tube, pipe, but good to write the way it has been produced, whether it is a forged tube, whether it is a cast tube, whether it is a rolled tube, whether it is an extruded tube, pilgrim tool tube, or similarly the plate, the way it has been formed, cold rolled, hot rolled, how many passes it has been given, to which specification it is meeting, which is already covered on the top. But if it is not listed, then better to write all these things in our WPS, either in this slot here, or we can put an annexure to our WPS and describe that form in a particular way, because some of the materials are very sensitive, from forging to plate to extrusion to casting, and the direction of the rolling also becomes sometimes, or the grain size also becomes important for achieving the properties, and even certain cases even the defect or the corrosion properties or the metallurgical properties of the joint. Base material dimensions are given here. These are mainly to understand what size of plate we have taken. Thickness is surely to be noted down, but what kind of a mass we have taken, especially when we are talking about high conductive materials or materials which has very low coefficient of expansion, the distortion levels, heat accumulation may be completely different, and the learnings what we want to take it here in this WPS PQR as to how the weld is going to behave, not only the property wise but also dimensionally and overall characteristics of that weld. It is good to list down the complete dimensions, like here it has been written down, the length is 500, weight is 500, thickness is 30, pipe also OD, ID, and the length is written down here. So it gives us idea of what kind of a material we have welded, what was the mass. We will be doing WPS PQR on this kind of a smaller pieces, but the equipment can be quite larger, quite massive, quite heavy on the heat extraction capability, and in that case, even though on a WPS plate our preheat of 50, 60, 70, 100 degree may be good enough, and the interpass will be asking to monitor, but in the reality the preheat may be inadequate because of the mass, and the interpass temperature, because of the mass which is going to extract heat, will never be touched. So all such things will get a good idea when we will be reviewing it after the WPS PQR is qualified, and when we have any non-conformances on the job, or how to really correlate and anticipate. So that is all given here. Thickness, as I said, is the essential variable, so we have to record it, and the type of joint, whatever is there, that also is required to be recorded and monitored. Pipe range or the thickness range can be specified, but within the code limits, and if we have used any particular process or a parameter which is very specific to a limited range than what the code allows, then this is a time where we have to write it, that even though code allows, we are further squeezing it, the tolerance based on our experience or based on the criticality of the properties which are required to be achieved, or based on the expected distortion levels, structural integrity levels, NDT levels. So accordingly, this range can be overwritten by us, and it is not that code says that you can go to 1.5 times the qualified thickness, 2 times the qualified thickness, or half of the qualified thickness, but we are the boss when we are writing it, and we can surely within the range but can squeeze and make it more stringent. The next is consumables, which is covered in our filler wire, filler metal. Once again, for which process what consumable we are using, we may have a different consumables for different processes, and that has to be written down. At least the nomenclature changes even if the chemistry remains same. For electrode it is E, for the TIG wires it is ER, for MIG and TIG we follow almost similar thing, so similar, but if it is a flux code then it becomes T1 or other kind of a nomenclature which is used. So good to specify F number, which is once again given in this WPS which is in front of us as NA, because we are going to use a non-standard consumable which is not listed in the section 2C, and that is why it is the SFA number is not applicable, but we have given AWS. Once again we have given the grade what we are using, and F number and A numbers are again written down as a not applicable. Now what is F number? F number is a purely the metallurgy of the consumable what we are using, or the resultant metallurgy which you are going to get into the weld. But A number is different. Even though I said the resultant of weld is covered in F, it is undiluted. That means when we are going to have a bid-on plate, after the 7th or 8th layer, the properties or the chemistry checked for calculating the F number. But in the reality, we cannot deposit so many runs, and there will be a dilution from both sides of the parent metal. So the resultant chemistry is classified into A number. So there is a slight difference. If it is a dissimilar joint, then A can be completely different than the F. That is, the weld chemistry could be 309, that is highly austenitic stainless steel, but your resultant chemistry may or may not be highly austenitic like 309, which has 20-25% of chromium nickel, but it can be 18.8. The nickel chromium percentage comes down to 18.8 because of the dilution of a carbon steel plate which is coming either both sides or one side, and that dilution, depending upon how much melting we are going to have on both sides, we are going to get the resultant chemistry, and that is what is listed into this A number. So F number and A number are once again very important, very critical, and requires to be noted down if we can classify into section 2C. But if not, we'll have to write NA, and whenever we are writing NA, that means this WPS is very, very specific to this material and these consumables, and cannot be used for the other ones unless we prove that these two materials are very close on their behavior and property wise. But for special materials which are not classified, it becomes difficult between a manufacturer and customer to agree upon, and good to have different WPS PQRs for each of these special alloys. Now, deposited weld metal thickness, how much material we are depositing? Are we fully covering up the 30 millimeters, or we are going to cover it only a partial, and we want to have only root side tensile bend, and upper side is assumed that it is going to be same, so we don't fill it up. In the fillet it becomes more important because a plate thickness can be varying from 5 millimeters to 100 millimeters, and the fillet could be a fillet of 5 or 10, that is the throat of the fillet could be 5 millimeters or 10 or 20. So both are required to be listed down, because that becomes a good document to review subsequently when we want to use a same WPS with another set of grooves parameters, whether are we going very close to it and nearby to our requirements. Filler metal product form, how the filler wire has been used, whether it is a coated, bare, flux core, does it have any synthetic additions of the alloying elements. All that is required to be listed down here, and don't go only by the electrode specification E7018 or E308L. See to it that you write down what is the composition of the bare wire and are there any additions through flux. Flux is supposed to be used only to create a neutral atmosphere and protect the liquid metal interacting with the oxide by having a layer of slag or a flux. So that's the importance. Hence, as much details we can write down in WPS are better. Let us not try to generalize our WPS. That helps only in non-critical or very standard fabrication, where even AWS kind of a codes are giving you permission to use a qualified material, qualified consumable, calibrated machines and a qualified welder, but do only WPQ mock-ups, that is welder's qualification or procedure qualification for the minimum gap, maximum gap, minimum angle, maximum angle, and ensure that your welders are able to demonstrate within the parameters which you are going to set it for yourself. But otherwise you don't have to do WPS, PQR separately. They are all pre-approved. So when it is a pre-approved, it's good. Code is giving us that permission, but always we gain a confidence by doing and spending a little money upfront, because it is not only achieving properties. I think it is finding it out what kind of a setup requirements are going to come. Can we penetrate in a gap of 2 millimeter with the set of parameters what we have chosen, or how are we going to really get the distortion levels, what kind of a fixturing is required for this joint. All that information, very good information, comes in handy when we have our own WPS and PQ. The next, of course, the very important is the position in which we are going to do it. The down end position where gravity is going to help us, the vertical position where the gravity is going to help us only 50%, the overhead position where we are going to weld completely against the gravity. So it becomes very essential variable, and welder's qualification also becomes essential if we are going to do the non-favored, that is 1G, 1F, 2F positions. Other than that, very essential to have a welded plate in different positions in which we are anticipating job to have essential thing, or job is going to demand that kind of a qualification which is going to come. Before we close this video and take a break, we will finish the post-weld heat treatment. Post-weld heat treatment is after the welding is done. Are there any requirements for us to achieve certain properties and give more confidence to our customer? Like for a carbon steel, alloy steel, martensitic ferritic steels, or even sometimes for titanium alloys, it becomes essential to drive away all the dissolved gases, soluble gases into that particular material, and especially the hydrogen, which is the tiniest gas and can move even at room temperature and gets accumulated in the cavities, porosities, or any metallurgical imperfection, and can create a higher pressure and create a small notch from this. Small rounded indications also can have a tail coming out if there is a hydrogen accumulation, which is called as a hydrogen crack, delayed crack, cold cracks. And to remove that, plus the stresses as the weld is going to be in the liquid form and going to shrink, we cannot avoid the shrinkage stresses in the weld, and that's the reason deciding a post weld heat treatment, whether it is solutionizing, whether it is stress relieving, or if we want to achieve certain properties. So are we going to do some aging, are we going to do some hardening, other heat treatment procedures which are going to either increase the strength or soften the weld and increase the ductility, toughness. So it is essential to consider a post weld heat treatment also for the joints which are critical to our equipment, and specify that in the annexure as to what heat treatment we are going to do it. And the post weld heat treatment, as we saw it on the top, can be part of this, that immediately after the welding, don't allow weld to cool below interpass temperature or below what your specified temperature, and heat it to that, so that the hydrogen gets a movability to move out of the weld, or if it has to accumulate, can go and accumulate in any of the imperfections, non-conformances, and have a resultant impact, a crack or distortion immediately, so that we can take a corrective action rather than getting it suddenly after some days or some time is lapsed. So that's why heat treatment becomes a very, very important to consider, and for all our critical equipments this is must. We cannot assume that I will be able to, I have lot of machining allowance and let it distort or let it have some other shape. I will correct it by the machining allowance I have kept it. But we forget that when we do that, already the joint is stressed, the equipment is stressed, and we are going to further stress it by machining. And after that machining, if we are going to do any work or assembly, at that stage this stresses shall not relieve, or over a period of time the stresses shall not relieve, or if the job has a high temperature application, the creep cannot get introduced and the stresses will become it more worse. So good to think all that beforehand. Then comes the gas, in case we are using a gas or a flux, in what flux type we are going to use it, how we are going to do that shielding. Is the shielding on the primary shielding, what diameter of ceramic we are using, what diameter of CO2 nozzle we are going to use it, or if it is a gasless wire, what diameter, what is the recommendation by the manufacturer for this. If we are going to use mixed gases, how are we mixing it? Are we going to use a pre-mixed gas? Are we going to have our own mixer? How are we testing the pre-mixed gas, or how are we testing the gas which we are going to mix it with our mixers? And then are we going to use any backup purging from the other side of the welding, and on the front side also are we going to give any extra shielding? Are we going to do a welding in a glow box or that kind of atmosphere? Are we going to create the particular atmosphere by using a box which is made out of titanium sponge or a nickel sponge? All these are becoming essential, and that's why we have dwelled upon this. It is not only specifying and just getting further onto it, as many details about purging. So if you are going to have a purging, how the purging arrangement has been done, whether there was a copper backup, then what diameter of the purging holes, at what intervals we have put, how many places we introduced argon. See, these are looking to be very tedious, time consuming, and what WPS I am writing in 15 minutes, the way I am elaborating here, it may take 3 hours, 4 hours, or sometimes even 2 days. But you will realize it once you go onto the shop floor if you don't specify and make it as a mandatory. Because once you write in WPS, supplementary, essential, or no non-essential variables, once you write, all of them are going to become essential. And if you want to change any one of that, you need to have a debate, if required a small mock-up, and then only you can really ascertain the impact of it. but is as many details we can catch up and as many details we can write in WPS. So it is only one time activity. With the latest technologies, this video and our understanding can be converted into a drop down menu for each of this, and we can make use of the digital technology. I'm not talking about AI, but using a better Excel or using a better Google form, by which when we are going to fill up each and every block of this or the variable in this, let there be a drop down menu and choose within those drop down menus over a period of time of, let's say, 6 months to 1 year. After undergoing 10-15 different equipments, our drop down menu will also become much more richer, and everybody will use a similar terminology or attach a sketch to bring a better clarity in this drop down menu itself, and uniformity will come into this. Now, like any other document, this document also requires approval, this document requires review, this document requires the revision dates and why that revision has been done. So I think in this last 35 minutes we have covered the first sheet of our WPS. We will take a small pause and then go on to the second sheet of WPS, and that's the way we'll cover WPS, PQR and WPQ and understand each and every function or each and every variable which has been listed here, which we need to enter, the importance of it, and how we have to write, to what details we should write, so that there is absolutely no confusion when we are going to execute on the shop floor. There will be multiple welders, multiple locations. Some of the activities can be even outsourced. So how to really pass on the information so that they will also follow all the instructions what we want on our equipment and the way our organization's culture or the quality systems are based. So thank you for listening the first part. We will have the second part very soon.